So in this video, we are going to discuss about second order low pass filter with variable gain. So what is second order means? It is a two-pole active filter. Active filter means we are using an op amp in addition to the resistance and capacitance. It is also called as Sallen-Key filter. So for low pass filter and high pass filter, we have used this one. Okay, so this is a general structure for second order low pass filter. You can see instead of a short circuit from inverting terminal to the output, I have used this RA and RF resistor. Okay, so if that is the case, this whole circuit it becomes a non-inverting amplifier, right? So I can write V out is equal to VB into 1 plus RF by RI, right? So this is nothing but VB into A. See, okay, this A is the gain of the non-inverting amplifier. Okay, so I'm going to apply the nodal equation. Okay, so for the node A, node VA, okay, for node VA, the incoming current is equal to outgoing current. So incoming current value is V in minus VA divide by the resistance. So here I am using admittance, so I am writing it as Y1. That is equal to VA minus VB into Y2 plus VA minus Vout divided by into Y3. Okay, so this is your first equation. The second equation for node VB. Okay, for node VB, VA minus VB into Y2, that is equal to VB minus 0 divided by, so into Y4. Okay, so I can write VA is equal to VB Y1, sorry, Y2, Y4 plus Y2 divided by Y2. So we have these four now we have these equations. So from what I'm going to do is I'm going to take this first equation, and from this I can write V1 Y1 is equal to V1 Y1 is equal to, I can move VA Y1 to the right hand side. So if that is the case, I can write as VA into Y1 plus Y2 plus Y3 minus VB Y2 minus Vout Y3. Okay, so now I can substitute the value of VA from this equation, from the third equation. Okay, so I can substitute instead of VA, I can substitute Y2 plus Y4 divided by Y2. Okay, so if I solve Y2, I can if I can multiply Y2 on both sides, I'll get this equation. Okay, so now I'm going to multiply this with this one. Okay, so I can write VB is equal to V out by V4, V out by A. Okay, so Y2 into Y1 plus Y4 into Y1 plus Y2 square plus Y2 Y4 plus Y3 Y4 plus Y4 Y3 minus Y2 square. Okay, minus V out Y3 Y2. So now I'm going to multiply this on both sides. So I'll get like this. Okay, so here I can cancel out these two terms, right? And I can also cancel okay, so I can write like this. So from this I can write V out by V in is equal to Y1 Y2 YA divided by Y1 Y2 plus Y1 Y4 plus Y2 Y4 plus Y4 Y3 plus Y3 Y2. If I take common, I will get 1 minus A. Okay, so I am going to divide the whole term by Y1 Y2. So if I divide the whole term by Y1 Y2, I will get A divided by 1 plus Y4 divided by y2 plus y4 by y1 plus y4 y3 divided by y1 y2 plus 1 minus a into y3 divided by y1. So since I am going for a low pass filter, I can substitute y1 is equal to 1 divided by r1, y2 is equal to 1 divided by r2, y3 is equal to sc3, y4 is equal to sc4. Okay, since I am using a low pass filter, so I am going to substitute this one. So if I substitute, I will get like this. Okay, so in that you have to assume R1 and R2 is equal to R and C1 and C2 is equal to C. So if that is the case, I can write A divided by 1 plus C. See here I can write it as 2SCR, and this one I can write it as S square C square R square, and this is nothing but SCR. Okay, so I can add this one. Okay, so I can write A divided by 1 plus 3 minus A SCR plus S square C square R square. Okay, so now I can write alpha is equal to 3 minus A. Okay, and omega h is equal to 1 divided by RC. Okay, so instead of RC, I am going to substitute 1 by omega h, and here also I am substituting omega h square. Okay, so instead of S, I can substitute as j omega. So, and if I substitute, I will get like this, and I can replace the real term and imaginary term separately, and I am going to take a modulus. So if I take modulus, I will get root of 1 minus omega divided by omega h the whole square into the whole square plus omega alpha divided by omega h of whole square. Okay, so here since alpha values root 2 for Butterworth filter, if I substitute here, if I take the whole square, I will get 2 omega square divided by omega h square. So here I am going to expand using A minus B the whole square formula. So if I apply, I will get like this. So here I can cancel out these two terms. So I will get V naught by V, that is nothing but h of j omega, that is equal to A divided by root of 1 plus omega divided by omega h the whole power 4. Okay, so if I want to represent, we know that omega is equal to 2 pi f. Okay, so here also you will get 2 pi omega h is equal to 2 pi fh. So here 2 pi will get cancelled out. So we will get A divided by root of 1 plus f divided by fh the whole power 4. So here A divided by 1 power root of 1 plus f divided by fh the 2 power n. So here in n is equal to 2. So I am getting 4 here. Okay, so this is the transfer function of the second order low pass filter, low pass active filter with the variable gain. So here if A is equal to 1, I will get unity gain, right? So I am going to take this fifth equation. Where is it? This fifth equation, V out by V in is equal to A divided by 1 plus j omega alpha divided by omega h minus omega square divided by omega h square. Okay, so I am going to take that equation, this one, and I am going to substitute this alpha is equal to root 2. See, j omega divided by omega h is nothing but here j omega divided by omega h is nothing but your s. So if I substitute, I will get this equation. So this is your h of s is equal to A divided by s square plus root 2. I can write it as 1.414 s plus 1. So this is for second order. This is a transfer function of second order Butterworth low pass active filter. Okay, So let me explain you a problem based on this one. So design a 2 second order Butterworth low pass filter having FH is equal to, that is upper cutoff frequency. Okay, so the upper cutoff frequency is equal to 2 kilohertz. So we know that FH is equal to 1 divided by 2 pi RC, that is equal to 2 kilohertz. So if I assume C is equal to 0.1 microfarad, I will get R is equal to 0.8 kilo. And we know that A is equal to 3 minus alpha. Alpha value is nothing but root 2. So A value is nothing but 1.586. So if A is equal to 1.586, we know that A value is equal to 1 plus RF divided by R1. So RF by R1, Ri value is 0.586. So if I consider Ri value is equal to 10K, RF value is equal to 5.86 kilo. So from this one, we know that C4 is equal to 1 divided by root 2 of C, and C3 is equal to twice C4, that is nothing but root 2 of C. So we have already find the value of C is equal to 0.1, right? So 1 divided by root 2 of 0.1 microfarad. And here also if we substitute root 2 of 0.1 microfarad, you will get the value of C4, C3 and R. Okay, so this is how the signal is, but here you have since it is a Butterworth filter, you have a distortion at the, so here I can tell this one as a pass band. Okay, up to this one, this will pass the value, and after that you have a stop band. Okay, so this one is called as transition band. Okay, and after that it will completely stop, no? So this is called as stop band. Okay, so transition band is between the pass band and the stop band. Okay, so if you see, since I am using a Butterworth filter, I can get some ripple at this point. Okay.